Good morning, students. Myself, Vaidegi, working as assistant professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject EC3452 EMF. The topics are from the Unit 4, Time Varying Fields and Maxwell Equations. In this lecture, we will study how electromagnetic waves are formed and propagated through space. We will understand how Maxwell unified electricity and magnetism into a single theory and showed that light itself is an electromagnetic wave. We will also discuss the engineering significance of wave propagation in modern communication systems. First, we see about the learning objectives. At the end of this lecture, you should be able to explain the concept of electromagnetic wave propagation and understand the role of Maxwell equation in describing electromagnetic phenomena. You will learn how electric and magnetic fields interact with each other, derive the basic wave equations, identify important wave characteristics, and understand real-world applications such as wireless communication, radar, satellite systems, and optical fiber communication. First, we see about the introduction to electromagnetic waves. Electromagnetic waves are disturbances that consist of oscillating electric and magnetic fields. These fields travel through space carrying energy from one location to another location. Unlike mechanical waves such as sound waves, electromagnetic waves do not require a material medium for propagation. They can travel through a vacuum. Electromagnetic waves are generated by accelerating electric charges. The examples include radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays. All these waves differ only in their frequency and wavelength. Next, we see about the Maxwell's equations, the foundation for wave propagation. The foundation of electromagnetic wave theory lies in the Maxwell's four equations. They are Gauss law for electric fields, Gauss law for magnetism, Faraday's law of electromagnetic induction, Ampere's Maxwell law. These equations explain how electric and magnetic fields are generated and how they interact with each other. James Clerk Maxwell combined these laws and predicted the existence of electromagnetic waves long before they were experimentally verified. Next, we see about the Gauss law. Gauss law for electric field states that the electric charges are the sources of electric fields. Positive charges create outward electric flux while negative charges attract electric flux inward. Gauss law for magnetism states that magnetic monopoles do not exist. Therefore, magnetic field lines always form closed loops. These laws help us understand the distribution of electric and magnetic fields in space and serve as the basis for electromagnetic field analysis. Next, we see about the Faraday's law of electromagnetic induction. Faraday's law states that a changing magnetic field produces an electric field. This principle is known as electromagnetic induction. When magnetic flux through a conductor changes, an electromagnetic force is induced. This phenomena is the operating principle behind generators, transformers, and many electrical machines. Faraday's discovery established the connection between magnetic fields and electric fields. Next, we see about the Ampere-Maxwell law. Ampere originally showed that electric current produces a magnetic field. Maxwell extended this law by introducing the concept of displacement current. According to the Ampere-Maxwell law, not only conduction current but also a time-varying electric field can generate a magnetic field. This addition resolved inconsistencies in my electromagnetic theory and completed the symmetry between electric and magnetic fields. This was one of the Maxwell's most important contributions. Next, we see about the formation of electromagnetic waves. A time varying electric field generates a magnetic field. Similarly, a time varying magnetic field generates a electric field. These fields continuously regenerate each other and become self-sustaining. As a result, the combined electric and magnetic fields travel through space as an electromagnetic wave. This mechanism explains how electromagnetic energy propagates even in free space where no medium exists. Next we see about the visualizing the wave propagation. An electromagnetic wave consists of three mutually perpendicular directions. The electric field represented by E oscillates in one direction. The magnetic field represented by H oscillates in a direction perpendicular to the electric field. The wave itself propagates in a third direction perpendicular to both E and H. Therefore, we say E is perpendicular to H and both are perpendicular to the direction of propagation. This makes electromagnetic waves transverse waves. Next, we see about the derivation of the wave equation. Using Maxwell's equation, we can derive the electromagnetic wave equation. The derivation involves combining Faraday's law and the Ampere's Maxwell law. By taking appropriate curl operation and applying vector identities, we obtain a second order differential equation. That is del square E is equal to nu epsilon dou square E by dou t square. The resulting equation describes how electric field varies with both time and space. This mathematical expression proves that electromagnetic fields propagate as waves. Next we see about the magnetic field wave equation. Similarly, we can derive the wave equation for the magnetic field. That is del square H is equal to nu epsilon dou square H by dou t square. The magnetic wave equation has the same mathematical form as the magnetic field wave equation. This indicates that both the electric and magnetic fields travel together as component of the same electromagnetic wave. The propagation speed obtained from these equations matches the experimentally measured speed of light. This was the major confirmation of Maxwell equation. Next we see about the characteristics of electromagnetic waves. Electromagnetic waves are characterized by several important parameters. The wavelength represents the distance between successive wave peaks. Frequency indicates the number of oscillations per second. Amplitude determines the strength of electric and magnetic fields. Phase describes the position of a wave cycle at a particular instant. Velocity represents the speed at which the wave propagates. These parameters are essential in communication and signal transmission systems. Next we see about the energy transport and applications. Electromagnetic waves transport energy through space. The rate and direction of energy flow are represented by the Poynting vector. The direction of the Poynting vector indicates the direction of the power flow. Electromagnetic wave propagation is used in numerous applications including radio communication, television broadcasting, mobile network, radar system, satellite communication, optical fiber links, Wi-Fi systems and modern wireless communication technologies. These applications form the backbone of today's information and communication infrastructure. Finally, we came to the summary of this lecture. Let us summarize this. Maxwell equations provide the fundamental framework for understanding electromagnetic phenomena. A change in electric field produces a magnetic field and a change in magnetic field produces a electric field. This continuous interaction creates electromagnetic waves that travel through space at the speed of light. The wave equations derived from Maxwell equations mathematically describe the propagation process. The principles discussed today form the basis of modern communication, radar, satellite and optical technologies. Thank you for your attention. The next lecture we will continue exploring advanced concepts related to electromagnetic wave propagation and application. Thank you.